Hello class 12. With this video, we are going to start alternating current circuits as I've already mentioned. And the very first kind of alternating current circuit that we discuss is a purely resistive circuit. This kind of a circuit contains nothing but only a resistor having resistance R, as you can see in this picture. And this is an alternating current source. This is the symbol for an alternating current source. You have a circle and you can see a sine wave inside it. Okay, so wherever you see the symbol, you need to understand that it's an alternating current source. Now, alternating current, we've already studied, changes its polarity, constantly from positive to negative, alternates between positive and negative side. So what is happening is, therefore, the direction of the current is constantly changing. At any instant, say for example, if this side is positive and this side is negative, because of which current flows in this direction, the very next instant what happens is, this side becomes positive, this side becomes negative, obviously because of which what happens is, direction of the current changes. Okay, and another instant again this becomes positive, this becomes negative. So this flipping of polarity constantly goes on, and thereby the change in the direction of the current constantly goes on. Now, at some instance, say for example, okay, this side is positive, this side is negative, such that current is flowing this way. Current I is flowing in this direction at any instant. Okay. So, current, as you can see, therefore at this instant, current is flowing in the clockwise sense. So what we can do is, in this circuit, we can apply Kirchhoff's voltage law. And let us therefore consider an anti-clockwise motion. Now do remember, the convention that we've stuck to regarding Kirchhoff's voltage law is that whenever we move in a direction of rise in potential, that is from lower potential to higher potential, whenever we move in this direction, we take the potential difference to be positive, and whenever we move in a direction such that there is a fall in potential, that is from higher potential to lower potential, we move in this direction, then we take the potential difference to be negative. Okay, so here we have chosen the anti-clockwise motion. So let us take this into consideration. Oh, by the way, I forgot to write the voltage of the instantaneous voltage of the power source is V naught sine omega t. Okay, this is the instantaneous value of the voltage, that of the source winding. So, considering this and considering anti-clockwise motion, we are moving from the positive terminal to the negative terminal. Okay, at this instant, we have considered this to be positive, this negative, remember. So we are moving from the positive side to the negative side, that is, there is a fall in potential, so to say, in the direction of our movement. So, whenever there is a fall in potential, it's taken to be negative, so therefore the potential difference across the power source is minus V, which is minus V naught sine omega t, of course, don't forget. Then after we encounter the resistor, of course, the only component then after left is the resistor. So, when we come across the resistor, the current is flowing in the opposite direction, of course. Okay, so we are moving from lower potential to higher potential. We are moving in a direction from lower potential to higher potential because current always flows from higher potential to lower potential. Therefore, the potential difference across the resistor is taken to be positive, which is I into R, and the sum of these two is 0 according to Kirchhoff's voltage law. So, from here we can write V is I into R, or instead of V we write V naught sine omega t is equal to I into R, and therefore I is equal to V naught by R into sine of omega t. Okay, now you can check this term over here, V naught by R. V naught by R has the dimension of current, because V by R according to Ohm's law also is current. Okay, so therefore instead of V naught by R, what we can write is I naught sine of omega t, where of course here I naught is V naught by R. Okay, so this is the value of the instantaneous current flowing through this purely resistive circuit. Now if we consider this equation, V is V naught sine omega t to be our equation number 1, and say this is the equation number 2, then from equations 1 and 2 we see that this angle omega t, over which sine of course is operating, this angle is the same. So to say, the phase angle of the current and the voltage in case of a purely resistive circuit, it's the same. So to say, in other words, the current and the voltage in case of a purely resistive circuit, they are in phase. Okay, so that is the conclusion that we can draw from this mathematics for a purely resistive circuit. And therefore, if we are to draw a phase diagram for a purely resistive circuit, you can pause the video and copy this of course. So let me erase this. I hope you finished copying. So if I am to draw a phase diagram, not phase diagram, phasor diagram, then if this is I naught having phase angle omega t, and remember I naught is rotating this way, also your voltage will rotate this way. They are rotating vectors, so to say, phasors. So this is I naught having phase angle omega t. So therefore this will be V naught. Okay, so to say the vector V naught is longer than I naught. Why? Because you can make out from this equation itself that V naught is bigger than I naught, because I naught is V naught divided by a positive factor R. So I naught is less than V. So this is I naught, this is a V naught, and you can see from the phasor diagram that both of these two things, V or V naught and I, the current, okay, both of the potential and the current, they have the same phase omega t, phase angle omega t, so to say. Alright, now what you can write here is, this is your I, or the instantaneous value of current. Likewise, this is your V, up to here is your V, up to here is your I, the instantaneous value of current and the instantaneous value of the voltage. Okay, why? Because if, say for example, you resolve I naught in the vertical direction. So if you resolve I naught in the vertical direction, what do you get? You get I naught sine omega t. And I naught sine omega t is what? It is the instantaneous value of current. Likewise, when you resolve V naught in the vertical direction, you get V naught sine omega t, which is the instantaneous value of the voltage. Okay, so instead of I, you could have written I naught sine omega t. Instead of V, you could have written V naught sine omega t. So this is the phasor diagram for a purely resistive circuit, and we can easily make out from the phasor diagram itself that both the current and the voltage in case of purely resistive circuit, they are in phase. Also, what we can do is we can draw a graph showing the variation of current and voltage for a purely resistive circuit. So if this curve represents your voltage, so to say this is V, which is V naught sine omega t, then this, so to say, is the peak value of the voltage. This is V naught. Okay, this is your V naught. Now we know for current I naught is lesser than V naught. So therefore, if I erase this, so this dashed line, it represents the curve for the current. This is I, which is I naught sine omega t. And you can see that the peak value of the current is lesser than the peak value of the voltage. Alright, so the solid line is representing the voltage curve, the dashed line is representing the current curve. Okay, of course you are plotting omega t along the x-axis, the phase angle, and both of these two goes on, and you can see for a purely resistive circuit from this graph also that the voltage and the current, they are starting at the same time, they're ending at the same time, so to say they are in phase for a purely resistive circuit.